Greeting AP Calc BC students. You're probably wondering what else is left? What else is there to talk about as far as Taylor series go, but particularly topic 10.15, which is about representing functions as power series. Well, we do have a few more things, and the first of those is going to be outlined in this video, which is all about integrating in order to find that series. So without further ado, let's take a look at our example number 6. Now the directions, at least the title, indicates that we are going to be finding a power series by integration. Now if you read the directions, it says let's find the power series centered at 1 for the function ln of x, and be sure to state the interval of convergence. Now I know that there are more than one way to do this problem. We could build this from scratch, and I'm not going to suggest that the way that I'm going to provide here is easier, or at least a shortcut. But perhaps for other series down the line, it might in fact serve as that shortcut. So kind of go along with me for the beginning stages of this, and let's kind of see how this goes. Now, it says that we want to invoke some idea of integration. Well, what that would mean is if we could say find a series for natural log of x, that's or if we could, let's say, not so much find the series for ln of x, but let's say if we could find a series for something whose integral is equal to the ln of x, that's what I wanted to say, then we're probably on track to have some success. But the problem is that we would still have to build the series for 1 over x from scratch, and then we would have to integrate its terms, so it doesn't seem like that is going to be much of a shortcut. I'm trying to see if I can avoid building the series from scratch, if at all possible. And besides, it doesn't look like I've got a situation where my series isn't centered at 1, or at least the function doesn't look like it's centered at 1, but that doesn't really matter a whole lot. And so I don't want you to overthink the look of the function and whether or not it's centered at where it should be. But what I want you to look at is the fact that we've been recently studying these very cool expressions that bear the form a over 1 minus r. Yep, those are those infinite geometric series that we've talked about, right? We know that this expression is equivalent to this particular summation, where n starts at 0 and goes to infinity. And we can use that, and have been using that, as a pretty powerful aid. The problem is this 1 over x doesn't quite bear the look of the 1 minus r. So what we can do instead is we could think about rewriting this 1 over x. Maybe we want that to be a 1 over 1 plus x. Now bear with me. I know that this doesn't have the minus for right now, but that's okay. But I do know that if I were to integrate that 1 over 1 plus x, I get the natural log of the absolute value of x plus 1, right? Now, I'm not going to make a super big deal out of using absolute values, and I know I probably should, and I'm not doing a very good job of using plus c here. And the reason is that I don't really have to worry about those things when it comes to thinking about convergence. And I don't have to think about the absolute values so much, because by the time I'm centered at 1 and I'm in this realm of positive numbers, I'm pretty sure that we're going to not need the absolute value. So let's kind of go with the flow for right now. Let's go ahead and think about this 1 over 1 plus x as being something that we could try to work with. Maybe we could try to find a series for it somewhat quickly. Well, we're going to be able to do that if we work this positive situation out and call this a subtraction of negative x. You've seen that in a previous video that we've done. And then hopefully you can see that this is just a geometric series where a is 1, r is negative x. So that just simply means we start with our first term 1, and we just simply multiply each term by negative x to get to the following term. Negative x times negative x would be quantity negative x squared. Just do it like that. And then the next term would be that negative x quantity squared times another negative x, which gives me negative x quantity cubed. And I have a feeling that you pretty much can see where this is headed. And as I said before, this is a geometric series where the a value is 1 and the r is going to be a negative x. Now, if you're wondering about the convergence here, right, of this particular series, we know that a geometric series will converge if the absolute value of its r is less than 1. Well, what that essentially means here is we extract out the negative 1 inside of absolute values, and it just goes away essentially. And then we just end up seeing that we will converge when x is between 1 and negative 1, and that would be exclusively. We know that we don't want to underline the endpoints because the geometric series convergence definition is strictly less than. All right, well, so what, right? What does this mean? Well, what this means is the natural log of 1 plus x, which is a series that we're sort of interested in. I know that it's not the end-all be-all series that we're interested in, but I think we're going to be able to connect the two functions pretty easily at the end of this problem. So let's start with this natural log of 1 plus x, and we all realize that that is just the integration of 1 over 1 plus x with respect to x. So what should we do about that? Well, I say we just integrate our expression that we have up here. And in fact, I'll probably go ahead and do a little simplifying with it as I write those terms. So it would look a little something like this. And if we do indeed integrate, we find that we get x minus 1/2 x squared plus 1/3 x cubed minus 1/4 x to the 4th. And if we keep things going, it's probably likely that you'll see a general term of negative 1 to the nth power. Notice how we start with a positive. So n would be our power for our very first term. Oh, I'm sorry, let's take that back. This is the first term, first power. So we want an n minus 1 or an n plus 1 there. All right, that way we got this to be positive. If n is 1, 1 minus 1 is going to end up being a 0. Negative 1 to the 0 is, of course, positive 1. And then we just have x to the nth to round out our numerator. And the denominator certainly looks like it's just going to be n. And I should say that this will plus dot, dot, dot go on forever. Now, what we're going to do from here is we're going to say, well, okay, that's all fine. All right, that's great. I can see that this has got some cool things going on with it, but I also see that this is very clearly centered at 0. There's no denying that. So it's kind of not centered where we want it to be centered, but it's also not the correct function. We want natural log of x. So my suggestion would be to say, well, if we want natural log of x, what is it that we can do with the natural log of 1 plus x to make it look like a natural log of x? Well, hopefully you're looking at this and saying, well, we would need to subtract 1. So what we can do is we can go into the natural log of 1 plus x and replace the x with just an x minus 1. And now you can clearly see that those two expressions that I've just written are equivalent to each other. Now, if we parlay that into the series that we just found, that would be this guy all over here. What we're going to do is go into him, and we're going to replace all of the x's that we see with, you guessed it, x minus 1. And so as we go through that and write, say, the first 4 terms at least, and some of you may have seen a typo here. That should be a 3. Maybe you're looking back and thinking, what is this guy thinking? Yep, sometimes it takes another step to catch your mistake, so I apologize for that. So many things go on with these problems at these higher levels. It's so easy to make a mistake. So then we have our nth term expression, which would very likely uh, keep the -1 to the n minus 1 because that's just a constant. And let's say the x to the n, we would just simply add 1, I'm sorry, replace the x, I should say, with x minus 1 there as well. And we have our nth term. And of course, this thing, I suppose, would go on forever if it was equivalent. So what have we got? Well, let's take a look. Look at the left side. Okay, we have ln of x, which is what we were trying to equate. And then look at the right side, or the very end. We have an nth term expression. And an nth term expression just simply needs a summation symbol in front of it in order to turn it into a full-blown, formal-looking series. And that's exactly what we're about to do. We'll rewrite that expression. As we do, I want you to all look and ask yourself, is it centered where we would like it to be centered? And of course, that answer is a resounding yes. And at this point, we know that we're going to end at infinity. We just have to come to the realization that we would like our n to start at 1. You really can't let n start at 0. It's probably going to cause some issue there. But if you do let n start with 1, it's very clear that you're going to reach this first term, x minus 1. Now, the directions did say, be sure to state the interval of convergence. Well, the fact of the matter is, if we had already determined that 1 over 1 plus x is convergent between -1 and +1, what does that say about, let's say, the interval of convergence for this guy? Well, I don't think you can say the convergence is between 1 and -1 so easily, and I wouldn't go there if I were you. And that's simply because we are centered here at 1. Now, I would like to go ahead and formally find this by using the ratio test, which I know the problem's been a little lengthy. We're going to kind of extend that just a little bit with the ratio test. But let's go ahead and see what we've got here. We're going to take the limit as n approaches infinity of the absolute value of the nth plus 1 term, which you can see that starting to take shape right now. And we're going to multiply that by the reciprocal of the regular nth term. Okay, once we've done that, where to next? Well, we're going to simplify. That's where to. So we do the simplifying, and we see that -1 to the n divided by -1 to the n minus 1, by the time you subtract those exponents, n minus quantity n minus 1 is actually a first power, +1, so it's going to stay up on top. The x minus 1 to the n plus 1 over the x minus 1 to the n is an x minus 1. Nothing that we can do about the n in the numerator, and nothing that we can do about the n plus 1 in the denominator. But what we can do now is we can see that the -1 in the absolute values is not going to play a big role, as he's going to become a +1 when we factor him out. The n over n plus 1 can stay together and in just a moment provide us with an answer to that limit, just as the x minus 1 rests along its own, and it will be also in absolute values, ready to provide us a limit. And those limits would be 1 for this guy. We've seen that many times, right? The degrees match there. And then the absolute value of x minus 1 here. And we know we want that to be less than 1 in order to converge. which means -1 is less than x minus 1, which is less than 1, which in turn means 0 is less than x is less than 2. So what has happened is that your interval of convergence that was up here at -1, 1 basically shifted over to the right 1 unit because of the replacement of x with the x minus 1. Now, had we seen that initially, we most definitely could have used that to our advantage, but now we know. And I'm just going to go through the motions and we're going to check these endpoints just to make sure that they're doing what they're supposed to do. I'm going to check the right endpoint here first. So we have -1 to the n minus 1 times 1 to the n over n. And as you can see, this is going to be the alternating harmonic series. And we know that's going to diverge. On the other hand, if we check 0, we get a little bit different result here, right? Kind of being a little careless about my summations and that I'm not being quite as formal with them as I probably should, where I start with n equal 1 and go to infinity, and heck, I'll just go ahead and do the same over here. That way I can sleep at night here. And then we end up with this expression all over n. And at this point, if you do some simplifying, and it's likely that you're going to see this relationship before this simplification is done, but this will just prove it to you. This -1 to the n minus 1, you can extract this out and make it -1 to the n over -1 to the first. Now, the reason why it's divided by is because of the minus there, right? We would have to have subtracted those exponents. And then we have a -1 to the n up here over n. And basically what's going to happen is that your -1 to the n powers will multiply, and you'll get +1 to the n. And essentially what you have is the -1 over n harmonic series, which we know is going to diverge. And man, am I messing up because I wrote the wrong word over here. Good thing I catch these mistakes. But the alternating harmonic series is going to converge. It actually conditionally converges. So now we've got our conclusions. Apologize for the confusion there. At least we got it cleaned up before we write the final answer. But at 2, we're going to converge. So that means we'll put our underline there. And at 1, or 0, I should say, we're going to diverge. And so this would be our interval of convergence, and this would be that power series. And there we go. That's how you can use integration to find a power series. As I said before, sometimes it's probably going to be easier, and I will be the first to admit, if we were to have built this one from scratch. Let's say that we just worked the original problem and took several derivatives of natural log of x and then centered him at 1, we probably could have found this a little faster. But we have an example coming up in the next video where that may not necessarily be the case. So we want you to stick around for that. Thanks for joining, and we'll see you next time.